I'm very excited to be here with Doug Rosenberg, who is one of the other co-authors with myself on this new book that we just released that is titled AI Assisted MBSE with SysML, an Integrated Systems Software Approach. So, Doug, thanks for joining today. And why don't you start out telling us a little bit about the book and step through a little bit of the outline of the chapters so some of the people who may not have picked up a copy as of yet will have an idea of what they can find in the book.
Sure. Well, thanks, Brian. I appreciate you hosting me here. So I thought we'd just kind of walk through the table of contents first in this video. And I want to start sort of with the subtitle here on the cover, which is an integrated systems and software approach. And one of the things that's different about this process than other processes like USM and Magic Grid that you may have heard of is that with AIM, we're holistically considering software as part of the systems engineering process. I think that's a totally critical difference between what this book is about and other uh, MBSE processes. So just to kind of scroll quickly through the table of contents, we're lucky enough to have a foreword by Professor Modney from USC. And he talks in the foreword about hardware software co-design and why that is an important problem that we're trying to solve. So as you see here in the preface, AIM is an MBSE process for hardware software co-design. And the premise here is that ChatGPT 3.5 came out maybe a year and a half ago. And one of the things that it immediately became very famous for is that it's pretty good at writing code. What we decided to do was to use AI and its ability to write code to solve the problem of systems engineers not really considering software. Then we go through a sort of an overview of AI. So Tim, who's our third author, wrote this. It's really a chapter, even though it's not numbered as a chapter. It's kind of a basic overview of AI. And one of the things that we do that's different is we use AI as a subject matter expert, and we'll talk more about that. So in chapter one, we talk about how to use AI in an intelligent way to do software and systems engineering. And we kind of introduce some personas for systems engineering. And what we mean by personas is this, that when you work with AI, it's not like calling a software function, you're having conversations with it. And if you give it a personality, then it's easier to have a conversation. In chapter two, we talk about really why it's critical to build our SysML and MBSE models to consider software as a first-class citizen. And it really simply is because no one is building systems without software in them. And so it doesn't make any sense to build models that ignore the software, right? It's like every system that is getting built now is software intensive. And so we treat software as kind of pretty important. One of the things we talk about in this chapter is functional decomposition versus object-oriented design. And we can get more into that at a later date, but the simplest reason that I prefer object-oriented design is that back in the 1990s, and I was around in these days, there was kind of a big battle between functional decomposition and object-oriented design. Object-oriented design won. Very, very few people design software with functional decomposition these days. And so if you want to align your systems engineering methodology with your software engineering methodology, it's kind of a slam dunk that OO is the way to go. All right, moving on to chapter three. One of the other motivations for this book is that SysML itself is changing. And SysML is changing with version 2, which has a language model in it. And because there's a language model, that means you can essentially specify a SysML model as code, right? Well, since AI writes code, that means we can teach AI to start generating SysML models. And Tim, again, our co-author on this, is right smack in the middle of the whole movement to version 2 of SysML. He's on the standards committee, and he's a really key player in that. So it's fortunate that we have him collaborating on this book with us. One of the things about this book that I think is important is that we use a single example all the way through. I've been teaching SysML for some years, and one of the things that drives me crazy about the teaching examples in SysML is that a lot of times, there's 9 different kinds of SysML diagrams, and it was too much work for people to put together one example that threads through all 9. So the examples kind of jump around, and I think it's hard
Right.
to learn that way.
Right.
So we design an electron microscope in this book, and we look at all kinds of different aspects of the electron microscope design, including the hardware, the requirements, the software, the parametric models. So everything in this book kind of ties into a single cohesive example. And we start out with domain modeling, and it's one of the big debate areas in the industry, which is domain model versus black box decomposition.
From what I've seen in the industry, a lot of times people want to jump directly into the functional decomposition, as you mentioned, and that's way before they've ever sorted out what the use cases are. So what you'll end up with, which is a term you've used quite a bit, is the deep trees of functions. And the problem with that you've always said you run into is the maintenance headaches. And that's very true because before you've even flushed out those high level functions, a lot of times people will begin, functionally decomposing those just to see how far they can go in that rabbit hole, and that really is a big problem because then you end up with a lot of misaligned levels of functions. You have functions that are maybe at one level that connect to some function at a lower level with object flows and things like that. And it becomes a big disaster. And that's a problem I've seen in the industry quite a bit.
In part 2, we talk about domain modeling, use case modeling, and requirements modeling. And in fact, there isn't a fixed sequence of where you start with all this. You kind of bounce around and trade off the domain model versus the use case model versus the requirements model. And I always think of it a little bit like if you ever change the tire on a car, there's all the lug nuts on there. Well, you don't tighten one of them all the way down first, right? And then go through the next one all the way down. You kind of go around in the circle
Right.
and you tighten them. And
Star
that's how
pattern.
you go through this conceptual modeling phase
Right.
is you do some domain modeling, you do some use case modeling, you do some requirements modeling, and you zigzag back and forth. In terms of the sequence, and do you do the use cases and the domain objects first? I always start with the domain model for this reason right here. And this is one of our personas that we introduce in the book. We call him Obi-Wan, which was actually a nickname that I gave myself. But the reason you actually start with the domain model is that it defines the vocabulary like a project glossary, right? And
Right. Right.
you have to get everyone talking the same language really before you start thinking about use cases or or requirements even. You want everything named consistently.
Right. Right.
So so we start with a domain model as opposed to a black box. And then we go into use cases and we employ use cases in a different fashion than, for example, they are used in something like Magic Grid. In Magic Grid, the use cases are used as a front end to functional decomposition,
Yeah.
right? So if you look at the Magic Grid grid, and the grid in Magic Grid is a great presentation. I love it. The functional decomposition, I don't love as much. Okay.
No.
But in Magic Grid, they use, they'll draw a use case diagram and then they're going to immediately start functionally decomposing those use cases.
Yeah.
We use use cases in a different way, and
Right.
that is we use them to identify the alternate and exception behavior of
Yeah.
the system. And that's the thing, I've been writing about use cases for an embarrassingly long time, around 30 years. But what people often skip with use cases is they don't focus on identifying the alternate and exception behavior of the systems, and
Right.
that's where things go wrong. I like to use use cases to kind of address the things that might go wrong and prevent them from going wrong, right? So it's more
Right.
preventative maintenance rather than fix it after the fact maintenance. And that especially makes sense when you start considering the use cases and the requirements. Um, because one of the prompting techniques that we use in requirements is to prompt for what are the possible failure modes, right?
Right.
So we're using AI as a subject matter expert for our electron microscope. Well, it turns out AI has lots of domain knowledge about lots of things.
Yeah.
It can tell you, oh, well, here's where things might go wrong here. And I guess the other thing that we maybe haven't mentioned yet is that in all of our chapters, the chapter ends with here's a table of all the prompts that we've used.
Right. Right.
So this book, as we go through all these chapters, 14 chapters, at the end of each chapter, there's a table of all the prompts.
Yeah, that's one of my favorite parts about this book is how is there's a wrap up of all of those prompts for each chapter. So it's a nice way to say, oh, this is exactly what we asked it to do for us, and that's how we got all of this great information out.
So, okay, that kind of wraps up part two. And then in part three, we start getting into kind of the meat and potatoes, hardcore systems engineering stuff, which is logical architecture, physical architecture, and parametrics.
Right, right.
Um, and if you start from a domain model, it turns out that your logical architecture just really tends to fall into place.
Right.
And I think this is a big difference from what we're teaching in this book to how a lot of people are currently doing their systems engineering. They're trying to take a black box, functionally decompose it, and then
Right.
somehow come up with an architecture for that.
Right.
And
Exactly.
as you and I have shared privately, decomposing black boxes is difficult, right?
It's
Because you can't
difficult.
see inside the box. So how do you decompose it, right?
Right, right.
But if you start with a domain model and say, well, here's the parts, okay, then it becomes very easy to come up with a logical architecture. And
Yeah.
there's a really simple way to think about logical architecture and physical architecture, and that is once you start thinking about subsystems, you're putting together your logical architecture. So you
Right.
identify all the subsystems, and then you go into each subsystem and start decomposing it, right? So I
Yeah.
call this recursive subsystem decomposition. And
Yeah.
you keep decomposing your subsystem down until the parts that you've identified for that subsystem are at the component level.
Yeah.
And that tells you when to stop. And
Right.
again, as you and I have shared a lot over the last year, year and a half, um, when do you stop with functional decomposition is a difficult question, right?
Right.
As you call them, rabbit holes. You start going down this rabbit hole
Right.
of functional decomposition. The other
Right.
thing that's interesting, and we can start tying it back to software, is that uh, once you identify your subsystems and start decomposing your subsystems, most subsystems are going to have some kind of control algorithm. And that control algorithm is generally going to be expressed as a state machine.
Mhm.
And with most systems that are being developed now, those state machines are going to be realized by microcontrollers
Right.
and microcontroller code.
Right.
And one of the things that I think probably surprised both of us as we were putting this example together is how good AI is at taking a state machine and
Yeah.
generating microcontroller code for it. But there's just kind of a very simple way to think about it, which is, um, you have conceptual stuff, which is problem space, and then you move into the solution space, and the first thing you do is attack your subsystems and figure out your subsystem decomposition. And then the next thing you do is when we get to the physical architecture and you decompose things down to a component level,
Yeah.
then you typically go out and look at real world components.
Hmm.
You do some trade studies and you figure out which components, which physical components are going to satisfy the requirements for
Right.
that particular subsystem, right?
Right.
I mean, intuitively, it's just I think a much simpler way to think about it. So in the logical architecture, you're doing subsystem decomposition. In the physical architecture, you're doing trade studies and component selection.
Right. Yep.
Um, and then when you've selected your components, what do you do next? You want to do some parametrics to
Right.
check that the components that you selected
Right.
meet the performance requirements, right?
Exactly.
And
Exactly. Yep.
and that starts out with measures of effectiveness here, which we addressed in the requirements chapter. Um, and so we kind of illustrate this with for logical and physical architecture. We talk about the electron microscope stage, which is a platform that moves the sample around under the electron beam. And then in the parametric stuff, we started looking at signal to noise ratio
Yeah.
and went through various attempts at what's the best way to model signal to noise and how do we improve the image quality in this thing.
Right.
And um, one of the things that we learned, or at least that I learned during this chapter, is that um, AI is actually pretty smart. And we wanted to do kind of a simplified uh, look at signal to noise ratio. And AI started lecturing us on the proper signal processing physics.
Right. Right. Yeah. Went a
And
little bit further than we wanted to go.
yeah, so it gave us like, 10 pages of here's why your physics is wrong.
Right.
And
Right.
then we're kind of like, well, we'd like to simplify this a little bit. And it's like, okay, you can do that, right? Help us do that.
Right. Yeah.
So that's the parametrics. And so, in these, I would say from chapters 4 through 9, we have a pretty good look at SysML,
Hmm.
all the 4 pillars of SysML: requirement structure, behavior, parametrics. They're all
Right.
covered. Okay.
Yeah. Yeah.
Um, but then here's where this book sort of leaves most everything else that I'm familiar with in the SysML world behind. And that is, now let's go carry this into software. If
So,
you consider, I guess we'll consider for the moment 3 SysML processes: USM, Magic Grid, and um, Rhapsody. Okay. Of those three, the one that that approaches software to a greater extent, a greater extent than the other two, is Rhapsody. Rhapsody goes through and it addresses sort of the embedded part of code generation,
Right, right. Yep.
which is sort of that microcontroller code from state machine stuff.
Right.
Uh, USUM doesn't really do that. Magic Grid doesn't really do that. Rhapsody
Right.
does that. Um, but what Rhapsody doesn't do is address things like database design and user interface design.
Mhm. Right.
And one of the points that we make in this book is that, yes, embedded code is important.
Right.
And we have a whole chapter on generating. The way this section of the book is organized is we kind of first survey, well, how was this all done beforehand? Right.
Right. Yeah.
And basically, we looked at two products that did embedded code generation, Rhapsody and Embedded Engineer, kind of compared them a little bit. And then we looked at one that I was involved with called CodeBot. And CodeBot was generating code for databases and user interfaces. Okay.
Mhm. Right.
We rolled those together into chapter 10 and said, well, here's a general overview of code generation. And then we have a chapter on each of these. And we have a persona who we called Otto Servo Magic, and that's Otto. And Brian, you work pretty closely with Otto, right?
Yeah.
And so and again with these personas, you're having conversations with AI about different sorts of things.
Yep.
And with Otto in particular, what we found out is that, and we had to kind of switch from GPT-3 to GPT-4 to do this because GPT-3
Yeah.
didn't read diagrams. Okay.
Yeah. The 3.5 version, right? Yep.
Right. And but once GPT-4 came out, you could just take an image, a JPEG or a PNG of a state machine,
Yeah.
drop it onto to Otto, and Otto will write you the microcontroller code, and you
Right.
just tell
Yep.
it which microcontroller code you want generated, and he knows about Intel microcontrollers and
Yeah.
Raspberry Pis and Arduinos, and
Right. Right.
he knows all that stuff, right?
Yep.
So you used to have specialists for each of these different microcontrollers.
Hmm.
It's kind of like now, you just say, hey, generate this code for the Arduino, and it does it, right? And,
Yeah. Yeah.
you still need to have a specialist to make sure the code works right and test it.
Right.
And that's the video you sent me actually last night, is that you've
Yeah.
generated from a Cameo activity diagram
Yeah.
are driving servos. And
Yep.
that's pretty cool, right?
Yeah. It's pretty neat.
And Otto wrote a lot of that code for you, right?
It wrote all of it. Yeah.
So, um, so that's kind of a little bit, a little bit revolutionary, I think.
Yeah.
And then chapter 12 goes into databases. And we introduced something called the MERN stack, which I happen to know more about because CodeBot was pretty good at generating MERN stack. And that translates into MongoDB, Express.js, React.js, and Node.js. That's where the MERN stack comes from.
Okay.
And we used AI in a little bit different way in this chapter, in that we asked AI to write a tutorial on MERN stack. And then, here, if I just go look at it, like, okay, give an overview of the MERN stack. And then our persona here is Cassie, short for Cassandra. And Cassie wrote us, like, there's a nice tutorial on MERN stack.
Think people who have various backgrounds are going to find a lot of things that they may have been familiar with, but maybe not known a lot about. And then a lot of people will find out a lot of things that they may not have been familiar with and learn quite a bit about. So there's a lot of that in here for everyone. So I think everyone, no matter what background you have, is going to find this book very, very fascinating and useful. and see how all those pieces get put together at that high level systems engineering view, which is what that's all about, right? So yeah, it's a great book, and yeah, please continue through the outline. I just want to say that because there's so many different people out there that have different backgrounds. Everyone's learning, and they're all in a different place right now. And one of those things that these authors bring to this table is just such a diverse background and experience in what you have in the industry. And so I think everyone's going to find it very, very useful.
Yeah, in particular, to just kind of to reinforce what you're talking about, most systems engineers have don't have computer science degrees. Okay,
Right,
so
right.
they're not necessarily. I mean, some do, right? Some systems engineers are good
Yeah,
with software, but in general, um, you can't really assume that systems engineers are well educated in software. And
right.
so in this book, we have some tutorials on kind of like software engineering for systems engineers, right?
Exactly,
That
exactly.
little tutorial. And, you know, the nice thing that allowed us to write the book pretty quickly is that AI happily wrote those tutorials for us. Right?
Yeah,
So I didn't have to go write a whole tutorial on MERNStack. I just wrote
right.
a prompt that says, hey, give me an overview of MERNStack. And there it is, right?
Exactly.
Um, so we address databases because almost all systems have databases in them. In our electron microscope, we have a database for image processing, okay?
Yeah,
Because the microscope produces imagery. And so you have to be able to save it, annotate it, mark it up, categorize it,
yeah,
enhance the image. So that's the part of the electron microscope that we use in these chapters 12 and 13. And we do sort of the same thing with user interface design here. And again, just to give an idea of what AI can do, let's list the screens for the electron microscope software.
yeah,
So, you know, I'm like, tell me about the user interface for this thing. And our subject matter expert for electron microscopes is a persona that we call Dr. Nano Micrographico. He's Italian. And we asked Dr. Nano when we have questions about the electron microscope, we ask him questions. So he said, well, you have to log in, you have a dashboard, you have an imaging preview window, you have import images, view screens, enhance the screens. Um, and then like here's a table of all the screens, right? So AI doesn't write perfect um, perfect code the first time, all the time. You have to have a conversation with it.
yeah,
And so, but my friend Meng Meng, who helped me out with the image processing, actually built out, we use an image processing library called GIMP. Um, and, you know, here he blurred the image. You know, you can increase the brightness, increase the contrast, right? So we
yeah,
didn't actually just sort of generate code and leave it hanging there. We actually built a database, pulled the images out of the database, did some image processing with them.
yeah.
So uh, we didn't want a lot of abstract theoretical stuff. We wanted stuff that actually works.
Right, right.
And then we went into software testing, talk about different kinds of testing, unit testing, behavior testing, selenium testing, which if you haven't heard of it, lets you actually simulate someone pushing buttons on a screen and pulling menus. This chapter was really interesting because AI wrote about 95% of this chapter.
Huh.
Most of the rest of the book we wrote, but in that particular chapter, we're just saying, show me what these test cases looks like. And it's writing all the test cases. And then kind of a last minute thing that we did at the end was we started translating into SysML version 2.
Right.
And our persona for SysML version 2 is called SysML or Sister Mary Lou. Um, and we took the diagrams that we had in the book and actually, if you haven't seen SysML version 2 before, this is some SysML version 2 code.
Yeah.
And again, we didn't sort of just generate it and throw it out there, but we went to this online SysML version 2 validation tool and made sure that the syntax was valid. So, we have use cases. Here's our logical architecture, physical architecture. And you can kind of see that the day when we're going to be able to code generate SysML models using the SysML2 language model is not very far away. In fact, it's sort of here already.
Right, right.
So that kind of wraps up the book. And again, the basic premise, I'm just going to go back to this one picture from the preface to kind of wrap up the discussion, was that this approach, AIM, is very much a common sense approach to systems engineering. And
Right.
the first part of the common sense is this list here. Number one, software is fundamental in systems engineering.
Right.
Number two, functional decomposition had its day in software engineering, but it kind of proved to be slow and cumbersome and hard to maintain.
Right.
And number three is, like it or not, we're in the AI era now.
Yeah.
AI is going to revolutionize our systems engineering processes.
Right.
And so we're starting with that in this.
Yeah, that's a great overview, Doug. Thank you for stepping through the chapter outline. Could you tell us a little bit about the cover, the book cover, and the image that we see with the robot shooting at the target?
Yeah, this was done with a very, very early version of ChatGPT 3.5 and DALL-E.
Right.
And I basically said, make me an image of an archery robot hitting the center of the bullseye. We decided, really what we're trying to do, right, is we're trying to hit the center of the bullseye with systems and software engineering. If you'd like to buy a copy of the book, you can get it at parallelagile.com/book.html. And it's available in 3 formats: ebooks from LeanPub, print books from Lulu Press, and Kindle on Amazon.